welcome again to the new lecture on properties of materials, and let us just briefly recap what we did in the last lecture. So, in the last lecture we started discussion on elastic behavior of materials. So, here we basically looked at what is the elastic behavior of crystalline solids, just a qualitative plot, and then of molecular solids like polymers. So, generally these exhibit small elastic strains and linear elastic behavior, whereas molecular solids show considerably large elastic strains and can show nonlinear elastic behavior, especially in materials like rubber. Okay. And here the elastic behavior which is in linear region, it is represented by this relation sigma is equal to E E. So, this is the stress. Stress is proportional to strain and the proportionality constant is modulus. So, this is called as modulus of elasticity or Young's modulus, and it has the same unit as stress. So, if stress is in pascals, this is also in pascals. So, let us not worry about mega or giga, they just if it is in pascals, this is also in pascals. There were few other quantities such as Young's. So, this is Young's modulus, then we have what we call as shear modulus and a log of elastic tensile strain or compressive strain, the shear, which is G is equal to tau divided by gamma. And then we have bulk modulus, which is basically related to hydrostatic stress, which is defined as K, and this is equal to sigma hydrostatic divided by delta V divided by V naught. So, hydrostatic stress divided by fractional volume change. And then another quantity that we defined was Poisson's ratio nu, which is ratio of transverse strain to axial strain or lateral strain to axial strain. So, axial is at the bottom and lateral or transverse is in the numerator. And then we were looking at the isotropic case of elasticity. So, basically so here let us say you have a bar which is elongated by a tensile stress, and this tensile stress gives rise to tensile strain. So, but it will also lead to contractions. So, as a result you will have tensile strain as well as you will have axial tensile strain as well as lateral lateral strain which is contracting in nature. So, as a result we will have epsilon x, which is sigma x divided by E epsilon, then we will have epsilon y and epsilon z as well. So, epsilon x because of epsilon y will be minus of nu E y, and epsilon x because of epsilon z will be minus of nu E z. Now, because of these strains, if you combine all the three components, then we have epsilon E x as sigma x divided by E minus of nu sigma y divided by E minus of nu sigma z divided by E, and this gives rise to relation E x is equal to 1 over E into sigma x minus nu to sigma y plus sigma z. So, this is what is basically you can say a general form of Hooke's law. This is where we were in the last class. So, this is called as general form of Hooke's law. So, this is strain, this is modulus, and this is the stress, overall stress that the material faces and giving rise to a net deformation. Corresponding shear strains are One can also get corresponding shear strains. Let us do them a little later. So, basically we have an expression for Ex. If we want an expression for Ey which will be similar, Ey will be sigma y minus nu into sigma x plus sigma z, and Ez will be equal to 1 over E sigma z minus nu into sigma x plus sigma y. So, these are corresponding equations for strains along x, y and z direction in the form of stresses, overall stress divided by modulus. Corresponding shear strains can be written as, one can write shear strains, let us say gamma xy, this is tau xy divided by g, one can write gamma yz, this is tau yz divided by g, and then we can write gamma zx which is tau zx divided by g. So, these are the three strains, shear strains that we have. So, the first three are tensile strains and the other three are shear strains. Now, let us say, now what we want to do is that we want to get a relation between the elastic properties. So, for example, how do you relate let us say the shear modulus and the bulk modulus. So, for this what we do is that we first consider the state of pure shear. So, assume state of pure shear. By this what we mean is that sigma x is equal to sigma y is equal to sigma z is equal to 0, sigma yz is equal to sigma zx, or you can say tau yz tau zx is equal to 0, and only tau xy is not equal to 0. So, this is the only finite component of stress tensor. Okay. So, if you now apply this to the principal stresses. So, we defined principal stresses earlier which are sigma 1, sigma 2, sigma 3 corresponding to certain axes 1, 2, 3. I forgot to mention earlier that this principal stress concepts basically relies on the choice of an axis 1, 2, 3 in such a manner, so that you only have sigma 1, sigma 2, sigma 3 without any shear component. So, there is no shear component. I think I forgot to mention this particular part when we talked about principal stress. So, basically sigma 1, sigma 2, sigma 3 are again normal stresses chosen on a axis system 1, 2, 3 in such a manner, so that there is no shear component and only the normal component remains. So, these are determined from this formula sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 is equal to 0, as we have seen earlier, and these i's are nothing but stress invariants. So, you can calculate stress invariants by looking at the formulas for them in the previous lecture, and if you put in these values of sigma x, sigma y, sigma z, sigma yz, sigma zx and tau xy or sigma xy in them, then we will find that sigma 1 will be equal to tau xy, sigma 2 will be equal to minus of tau xy, and sigma 3 will be equal to 0. So, basically after determining I1, I2 and I3 values by plugging in the stress values as we mentioned earlier, we will find this is the stress state. So, among three principal stresses, one is 0 and other two are equal and opposite. So, this is the basically, so when the material is in pure shear, then this is what the stress state is going to be. The principal stresses are going to be tau xy and tau. If you want to mention this, so this is let us say 1, this is let us say 2, then this is what the stresses are going to be like. So, in one case it is going to be tau xy and here it is going to be minus tau xy. So, these are the stresses which are going to act on the material. Now, when you apply these stresses to the Hooke's law, so the Hooke's law that we wrote, so now Hooke's law, if we rewrite that, this is equal to, so we can write in terms of principal strains. So, E1 is equal to 1 over E into sigma 1 minus nu into sigma 2 plus sigma 3. So, basically in terms of corresponding principal strains. Okay. So, if you now put in the value here 1 over E, this is equal to tau x y minus of nu minus tau x y plus 0. So, this will be tau x y divided by E into 1 plus nu. This is what your E1 value is going to be, and E1 is nothing but, E1 is nothing but E x y, or you can say epsilon x y, which is related to gamma x y divided by 2, as we saw earlier that mathematical strain is equal to gamma x y divided by 2. So, if that is the case, then if we write the expression for E1, then this becomes gamma x y divided by 2, this is equal to tau x y divided by 2 divided by E into 1 plus nu. So, we can see here E is equal to 2 into tau x y divided by gamma x y into 1 plus nu, and this is equal to 2 into G into 1 plus nu. So, what we get a relation here, the shear modulus is nothing but Young's modulus divided by 2 into 1 plus nu. So, this is a relation that we get between the two elastic properties, that is G, E, and three elastic properties G, E and nu. So, if you know E and nu, you would know G. If you know any two of them, you would know the third property. Similarly, you can derive a relationship between bulk modulus So, for bulk modulus we write this as fractional volume change as sigma hydrostatic divided by K, alright. This was the value of bulk modulus that we saw earlier. Now, sigma hydrostatic stress is generally given as, in a general form, is sigma x plus sigma y plus sigma z divided by 3. However, if we assume that volume strain is an outcome of a state of a particular state of hydrostatic stress such that sigma hydrostatic is equal to sigma x is equal to sigma y, and this also satisfy the above condition, but this is a particular case of hydrostatic stress state. So, this is a particular case. In this case, if sigma hydrostatic is assumed to be equal to sigma x plus sigma y plus sigma z, then we can write delta V by B for small strains. This can be approximated as Ex plus Ey plus Ez for very small strains, because for very small strains the true strains will, we are using E and epsilon repeatedly, but remember for very small strains. So, when we say earlier here, when we say E1 is equal to epsilon Ex or epsilon xy, what it means is that very small strains. So, essentially we are looking at very small strains where E is equal to epsilon. So, there is a correspondence between the two. So, similarly, this is equal to Ex plus Ey plus Ez for very small strains. So, here now we can determine what is Ex. Ex can be determined as 1 over E plus sigma x minus nu sigma y plus sigma z. So, now let us replace all these values here. So, this will be sigma hydrostatic. So, basically it will be sigma hydrostatic minus nu into sigma plus sigma hydrostatic. So, this will be sigma hydrostatic divided by E into 1 minus 2 nu. So, basically delta, and we are saying now this is equal to, essentially we are saying that, so delta V by V is equal to 3 times this, which is 3 into sigma. So, basically we are saying that delta V by V is equal to 3 times E x for a special case, for a special state when sigma x is equal to sigma y to sigma z, which means E x is equal to E y is equal to E z. That means delta V by V is equal to 3 E x, which means it is equal to 3 into sigma hydrostatic into 1 minus 2 nu divided by E, and this is equal to 1 by k into sigma hydrostatic. So, these two cancel each other. What we have a relation between k and E, which is E divided by 3 into 1 minus k is equal to E divided by 3 into 1 minus nu. If you combine this relation, so this is a relation which relates the bulk modulus, the elastic modulus and the Poisson's ratio. The previous case you related Poisson's ratio, Young's modulus and the shear modulus. So, naturally you can see here, if you combine these two equations you can obtain. So, combining relations yields nu is equal to E divided by 2 g minus 1. So, this is the third relation that you get between these quantities. So, this is what basically we have done. So, in this, so this is sort of a small short primer to basically elastic properties. So, essentially let me now come to sort of a summary of this particular part. Summary at this point, it is not the overall summary, but summary at this point. Basically what we did was we have looked at what elastic behavior is. Essentially when you plot stress as a function of strain, then there is a linear region before your nonlinearity starts, and this linear region is essentially, so this is, you can say, a linear region, and this is obtained for most of the solids, especially crystalline solids, metal, ceramics, etc. And this linear region will give you E, which is sigma divided by E. So, there is a difference, fundamental difference between the metals and ceramics that you will obtain. So, for metals you will have a behavior generally like this before material fails, whereas, so this will be for metals. So, they will show a pronounced region with the strains less than 0.005, very small strains, whereas for ceramics you will obtain basically something like this, and they will fail at the, so this is, let us say, A, this is B, this is O. So, this is for ceramics. So, naturally you can see the slope is higher, and as a result their modulus is higher, and we will see microscopic regions a little bit later. And for polymers generally you will see a behavior like this, very long, and this is where somewhere they will fail. So, this is polymers, and we see generally that E of ceramics in general is higher than E of metal, and which is much higher than E of polymer. So, this slope is very, very low in case of polymeric materials. So, this is what we will see later on in the, and then what we did. So, we from this we learnt about a quantity called as Young's modulus. which is valid basically for tension or compression kind of thing. Now, there are other values we looked at shear modulus, and we looked at bulk modulus. Shear modulus is G, bulk modulus is K, and then we looked at what we called as Poisson's ratio nu. All these properties, as we saw, they are interrelated, and so you can determine your shear. This is how you can determine your Young's modulus, but if you wanted to determine shear modulus as a function of shear strain, then of course you have a similar kind of plot before. So, this will be the G, which is equal to tau divided by gamma within, and if you wanted to plot the same thing for bulk modulus, you can say this is sigma hydrostatic, this is delta V divided by V naught, which is the fractional volume change. Then we have and this can continue further. The slope of this K is equal to sigma hydrostatic divided by delta V divided by V naught. And then we looked at the general form of Hooke's law, which says that E x is equal to 1 over E sigma x minus nu into sigma y plus sigma z. Similarly, you can write E y, this is equal to sigma y minus nu sigma x plus sigma z, and then we can write E z, which is 1 over E sigma z minus nu into sigma x plus sigma y. Okay. So, this is what we did for learning about the Hooke's law, and then we worked out the relations between G, E, K and nu. So, in the next lecture what we will do is that we will look at the atomic origin of elastic modulus and differences, which is basically related to bonding. So, we know that materials are basically you have primary bonding and you have secondary bonding. In primary bonding we have ionic bond, we have covalent bond and we have metallic bond, and in secondary bonding we have hydrogen bonding, van der Waals bonding, and so there are some other secondary bondings. In general, the energy of is much higher than secondary bonds. So, we know when you plot the potential energy, the potential energy goes something like this, right. So, this is W, this is R, this is the separation between the atoms, and this is the equilibrium separation, let us say R naught, and this y axis distance from minima, the distance of minima from the 0 is essentially you can say E bond. So, in ceramic materials generally this E bond is very high, and the energy the potential energy curve is much more shallow as compared to than in soft metals and polymers. So, we will see that the materials with higher bond energy and narrower energy, the potential energy wells, they have higher modulus as compared to the materials with smaller bond energy and broader potential energy wells. So, this is where we will stop today. We will continue this atomic origin discussion in the next lecture. Thank you.